So, hello everyone. I'm taking care of this part, introduction to Go. Golang, also known as Golang. Go is the programming language that the team picked as a choice when Tendermint was about to be developed in the beginning. And so we're going to give an introduction to the programming language, not just because it was chosen to develop Tendermint, but because it's the main programming language of choice. When you want to develop an application with Cosmos SDK, you can generally go with Go, because it's the programming language of choice of Cosmos SDK. So although the Tendermint is actually developed in a way that you can actually develop your application with the language that you prefer, when you want to use Cosmos SDK, you are encouraged to use Go, because Cosmos SDK is designed or written in Go. Now, so first, who am I? I'm from Rome, Italy, currently living in London, which is I think Italy's biggest, third city outside, second city outside Italy, the biggest one. Buenos Aires is the biggest one, actually, when it comes to number of Italians living in the city. I'm a long-time Frost contributor, and I just spotted the typo. Nice. Okay. Frost contributor, as in a free and libre open source software contributor. I've been in the Ubuntu community for quite some time. I think I started out roughly 14 years ago as a contributor to the Italian local team, writing documentation, wiki pages, and then I moved on, because I was already writing software professionally. I moved on packaging software for Ubuntu, then I moved upstream to Debian. Debian is known as the Universal Operating System. And then I participated in a number of open source projects across the globe. Then I spent the last 15 years writing software as a freelancer, systems engineer. I did work in advertising as well, embedded programming, sports gambling. I was the only non-quant in a team of quants, doing reconciliations fundamentally, and I always had a brief but intense stint in finance and banking, just before I joined the Tendermint team in order to contribute to the development of Cosmos SDK and for the preparation work of the launch of Cosmos App. So what I'm doing now, I'm taking care of partnerships and institutional relations across EMEA, so Europe and Middle East and Africa. I'm still contributing to the code base of Cosmos SDK and a number of even applications written by partners. So that's briefly nearly all about myself. So why Go? And why Go takes actually a very interesting answer. Marco before mentioned that Tendermint was built, designed to be simple. Simple as in transparent, no implicit tweaks. So we wanted developers to understand what they were doing and then to be in a position to read through the code and understand what the system is doing. And in order to do so, we needed, the team back in the day needed to find a language that was to some extent built with the same characteristics in mind. And Go is actually a product developed by Google, I think a number of years ago, 7 or 8 years ago. One of the designers of Go, his name is Rob Park, one of the person in computer science that I keep in the highest esteem, I would say. Also known as the spirit of Unix. So one of the people that actually invented Unix in the first place. And Go was developed by Google to solve, well, Google scale problem. So big, complex problem without, though neglecting simplicity. So without compromising on convenience, for instance. Always keeping simplicity in mind. Big hardware, big software. Hardware is a very important component. You will see that Go is, as a matter of fact, a mid, it isn't really a low-level programming language, but it's not even too high level. So it's a mid-level programming language. And one of the problems, one of the biggest challenges for modern times, of course, is scalability. And one of the biggest challenges in corporate environment is actually the development might at some point happen with a very slow pace. So one of the problems Google wanted to eliminate was slowness. The other one was clumsiness. So you want to develop software that is free of tricks and it can be elegant, but at the same time efficient and effective. So they wanted to improve productivity when it comes to engineering process and practices, and of course scalability of the software per se and maintainability. So one of the design principles of Go is the importance of locality. Locality means there are no hidden tricks in the language. There must be no hidden tricks in the way one designs software. You will notice that there are no explicit initialization, but at the same time there are no implicit constructors in the Golang basic data types. And Go, of course, in order to eliminate clumsiness and to some extent one of the limitations of dynamic languages. Dynamic type languages are very fast to get on with because you just write a few lines of code in an editor like Python, for instance, or Ruby, but you happen to develop something that might tend to be error-prone. So you want a static type system, but you want a simple type system, something modern as well. Very often Go is compared or actually called as a modern C. It's actually more than that. It is actually far more than that. And there was this intention to pair the power of a kind of low-level language with the simplicity of high-level language, like for instance Python. Many of the features of Python actually inspired some of the Golang features and design principles. So there were these three important characteristics. One is orthogonality. Go had to be simple, and had to be simple to design and write software with Go. So orthogonality means that there should be only one way to do things, as in the idiomatic way of doing things, so that you can build building blocks independently from each other, reducing the number of dependencies of one onto another. The language has to be simple, and the language has to inspire simplicity. So you will see Go, one of the next slides about object-oriented programming, whether Go is object-oriented or not. Go is object-oriented, and the answer is yes or no. In fact, there are no classes, and there is no inheritance whatsoever, because there is no type of hierarchy, though there are methods and there is composition. So Go is a sort of object-oriented, but it's very simple. It's object-oriented programming, but taken very, very, very simple. Readability is quite important. Readability is important to the end of maintenance of software. So you don't want any, for instance, one of the biggest mistakes of C, which was a conditional compilation, which makes code quite unreadable when the project grows in terms of size. So very high sound to noise ratio. No header files. Everything can and should be declared only once in each block or package, and you take it from there. You come up with a very readable source code if you stick to the Go conventional way, the Go idiomatic way of doing things. So this is a quote from Joe Armstrong. Go is, and Rob Pike especially, and his team is very known to be against object-oriented programming, but not object-oriented programming per se, but the way object-oriented programming was sold, if not oversold, over the years. And this is one of the reasons why, right? The problem with object-oriented language is that they got all these implicit environment that they can carry around with them. You wanted a banana, but what you got was a gorilla holding a banana and the entire jungle. This is fundamentally one of the problems that Go wanted to solve. So we want reusable code, but we don't want to hide implementations, we don't want to hide the state. Because, and I'm quoting once again, I think Pike, because the state is the root of all evil. So programs need to be designed with simplicity in mind and with readability in mind. Nothing should be hidden to programmers. So that's the question if Go is object-oriented. So there are no classes, but there are structures, very similar to C structures. Encapsulation, one of the object-oriented programming principles, is so information hiding is actually implemented by embedding. But there is no protected members in a Go structure or interface. And there is a very simple way to make things public or private. It's anything that starts with a capital letter is public. All the rest is private. Private either within the scope of a package or within the scope of a structure and its methods. So composition is preferred of inheritance. There is no inheritance. There is no single multiple inheritance. Multiple inheritance has always been problematic in the history of computer science. I would say not many languages got that right. If I take Python as an example, Python has this mechanism where there is an MRO, so multiple resolution order, when it comes to classes inheriting from multiple classes. And that makes things complex, not just complex, but complicated, and to some extent even unpredictable. There is no overriding. Polymorphism comes out of the box, and there is the concept of interface, which is very similar to the concept of interface in other languages, such as Java, for instance. And a type, you will see that there are no classes, but there are types. Types can actually implement multiple interfaces, but they satisfy interfaces implicitly, without declaring what interface they are satisfying. And methods that are attached to types, we will see how. Methods are fundamentally just functions. And I go. So in order to install Go, Go is pretty simple to install. To install the Go compiler, I need to Go, of course, is multi-platform, supports Windows, Linux, BSD platforms, Mac OS, so Darwin, and even runs on Plan 9, which is a quite interesting project run by Pike a long time ago. And it's pretty easy. You can download installer for Windows, installer for Mac OS, or for Linux. You just download the zip file and you install in a directory. And there are a couple of things, a couple of environment variables that need to be declared. Actually, with the latest version, you don't even need to declare a so-called Go path. You just download a zip file, you install in your system according to the instructions given on the website, and then you type very simply Go env, and then you get all the information regarding the Go compiler environment. This is, of course, the command to check the versions of Go installed. So yes, the binary we just seen is Go, and Go is not just the compiler. Go is a tool to manage the source code. It comes with a number of subcommands. Go build is the command to compile packages and dependencies. Go run is on-the-fly compiler and utility you can use to run programs on the fly. Go env displays information regarding the Go environment. Go test is the utility you use to run test suites and benchmarks. Go install is very similar to Go build, but then it takes care also of the installation of your binary. into the Go path hierarchy, directory hierarchy. Usually there is one directory. There could actually be multiple when you run the Go compiler called Go path. The Go path is the directory where usually modules and packages are installed by using the go-get command line tool that is used to download dependencies and packages from the internet. And usually the Go path has a structure which takes, I can show you this example, I would say it's better. I think I need to go my, this better. So this is my Go path, which could even be undefined. Go, in case of Linux, like in this case, would define your Go path as your user directory. So my user is Alessio, so my user home directory is /home/Alessio, this is Ubuntu, /go by default. The same pattern is used on Windows and Mac OS. So if I go into my Go directory, this is the high-level structure of the Go path. There are three directories, source, package, and bin. Bin is where Go installed, usually install the binaries of your compiled programs. Source contain the structure of your packages. We will see what packages are. And packages just contain archive information regarding the packages, and it's out of scope. It's something that it should be out of interest for the Go 101 course. So there is not much to be told about this stage about the package directory. Anyway, installing a package in Go, it's quite easy. You just use the command go-get, and then the path of the package. Go introduced this concept, this package manager, which is fundamentally it comes out of the box with a Go tool, and you just do go-get. You can use any. Go is capable to parse any of the most popular VCS systems, so you just give a URL without the prefix HTTPS of a package over the internet. And it doesn't really matter, it could be GitLab, it could be GitHub, it could be your private owned repository, it doesn't really matter. So for instance, I'm going to download the Cosmos SDK. I'm going to download one of the packages of Cosmos SDK, which is Types. And just do go-get, remove it. And go-get is installed in my package within the source directory, which is then made available for me to develop my programs with. So I go back to the presentation. Because there will be some examples at the end of this. Other examples is GoDoc. GoDoc displays packages documentation. This is quite an interesting thing to see. Go tries to inspire programmers to follow good practices, and one of the good practices is writing documentation along with the code. And when you stick to the Go idiomatic way of writing documentation, so writing doc strings before the declaration of function or types, Go will display this information automatically by the Go documentation. So GoDoc, I could go and do Cosmos SDK, name of the package. Okay, there's nothing here. I think. No, there is documentation. There's something wrong with my setup. Okay, let's go and see, for instance, one of the standard packages, which is Go format. FMT is one of the standard packages provided by Go, and these lines actually are in the source code of the package. and this is a way you can display documentation. Documentation can be displayed also through the GoDoc command, which is an external tool, which spawns a small web server and displays all the documentation available through your system, through the packages installed within your Go environment. And it's fundamentally this interface here. Spawns a web server like this one. And along with the standard packages that come with the compiler, you will see all the packages installed in your system. And this is one of the commands available with the Go tool. And this is the comprehensive list of all the packages, all the standard library fundamentally that comes with the Go tool and the Go compiler. So let's say let's go next. So I think I need to exit my full screen mode in order to visit the links and the examples that I prepared. So there is a Go, an hello world program that I've written, a very tiny one. Well, simple as that. There are a couple of interesting points that we need to cover. The very first line of a Go source file has to be a package declaration, which defines the name of the package within the source file living. And then there are import statements. So in this case, it's package main. This is to indicate the compiler that regardless of the name of the directory, this is the main package and will contain a function called main, which will be the main body of the program that will be compiled into the executable. And then there are import statements. Import statements, which define a list of the packages you want to use in your program. So this is a format package, which is a standard package providing formatting utilities and general purposes, functions and types for formatting output. And it's pretty easy. Function main, which doesn't return anything, and we will see why and how it works. And format println hello world. This is quite interesting because we are using a function that lives within the package format, and it starts with a capital letter. Now, anything in a package that needs to be exported, anything that is public and accessible outside of the package, has to start with a capital letter. And this is not just idiomatic, this is something in the compiler. So if you make a package, all the functions you want to be private, you just make them start, the name starts with a small cap letter. And we can, of course, import sub-packages as well. So packages can be organized. There could be a structure of packages and can be organized within sub-packages as well. So in this case, I can run this code. This is a website called the Go Playground, so you can go and write your code and try to run it quickly. This is pretty interesting. So I'm printing the usual hello world, and I'm also printing the printf function. I'm utilizing another function from the format package. And I'm using a random number generator from the rand package, which is a sub-package of the math package. And as such, I'm not going to use anything else but just the name of the last component of the path of the sub-package. So math/rand, I just use rand and call inten. I call inten and 10 as a seed to create to print a pseudo-randomic number. Then there is also another way one can use imports, which is the so-called dot imports. Fundamentally, it's exactly the same example as before, but rather than importing rand and use all the functions and the types within rand by prefixing their name with rand dot, I'm importing rand into this visibility scope into this file visibility scope with a dot operator, which means import everything which is public within this package, so I don't have to use the rand prefix.
Just out of curiosity, is it tab sensitive?
Sorry?
Is it tab sensitive like Python?
Absolutely.
Okay.
Yeah, absolutely. Yes. It's absolutely case sensitive.
No, not tab sensitive.
What do you mean by that?
Tab.
No. Okay, no indentation. No, it's not like Python. The recommendation, which can be enforced by using a command called go format, is tabbed instead of spaces. Okay. And there is a very simple reason, which is quite funny, but it's like one tab is less expensive than 8 spaces, because it's 1 byte instead of 8 bytes, which makes sense. And so you have a degree of freedom, but you don't want to abuse of that freedom. That's why all the syntactical rules and recommendations, actually most of them don't need to be followed, but you can use automatic tools to reformat your code automatically. I can show you an example later. There are multiple formatters. There are spell checkers. There are syntax checkers as well. They can raise warnings and gives you suggestions on how to improve your code. Most of them can actually fix your code automatically. So there is, it's very much like the tool like Pep8 or PyFlake with Python, okay. But they are designed to fix your code automatically. Most of them, at least. And there is an important thing that we should actually cover. I'm going to import another package. I'm going to import the package math without using it. This is a compilation error. You don't import anything that you don't strictly need. And this is something that these automatic tools, when integrated with your IDE, they will get rid of this line automatically. And it's not just code hygiene, it's proper compilation error. So as I said before, anything, functions, types, variables, constants, everything that starts with a capital letter can be exported from a package. All the rest is fundamentally private, and it cannot be used outside of the package, but within the same package, yes, they can be used. Next. So, yes, let's get on with some examples about flow control. So we have the most classical statements, so if else, and this is a branching with a if and else in Go is very simple. This is a package declaration, which has to, as I said before, has to be on top of your package source files. Then there are all the import statements you want to use, even though you don't have to group these import statements as I've done before. You can actually have multiple lines. I will show you more examples about this. But this is an example which focuses on the if-else construct. So if condition, parentheses or brackets, and which is mandatory in Go, else. You can have an if statement without an else, of course, and you can have a branching like this. Now, this is quite interesting. A statement can precede conditionals, so you can declare a variable and assign a value before the condition of the statement is actually evaluated. So in this case, you have if num. This is an assignment declaration, called a short declaration. equals none, if none less than 0, etc., etc. But this variable it exists only within the scope of this if-else statement and its branches. Outside of here, it doesn't exist anymore. So if I were to print none here, I will get a compilation error. Oh, I didn't use types here. Undefined none. Same thing happens with variable declaration if I define a variable and I don't use it. Declared and not used. So the language is pretty strict. You don't need parentheses here to wrap the conditions. You really don't, but the brackets are mandatory. And there are other, of course, there is a switch. Switch statement where you have fundamentally different conditions and across many branches. So you can have the switch here, it's pretty simple. So you have a switch on a variable called e. In case it's 1, you print 1, etc., etc. There is a statement. In case you want to go fall through one case to another, this statement is this statement is called fall through. So you evaluate 2 and then you evaluate 3. This is a fall through statement. There are also, this is a type switch, which we'll see better later on, because we haven't yet introduced type in interfaces, so I'm not going to cover this now. There are empty switches, which is an alternative way you can express multiple if-else branches, and it's actually recommended to use an empty switch without an expression fundamentally, because it's more readable than writing if-else all the time. Then we have a for loop. I'm going to cover this quite quickly. Okay, this is the only looping construct available in Go. There is no while, there is no do while, there is nothing like that. So there is only for, and there is the most basic type, which is just a for with a looping condition. Then there is the C classical initialization condition after for loop. This variable is initialized at the beginning of the loop as initialization, and it's available, as I said before, only within the for statement, this for block. This is a never-ending for loop, and then you can end the loop by breaking the statement. And then of course there is even the use of the continue statement. It's pretty much like C and Java and Python, so it's fundamentally the same thing. And we will see for usually is used with a statement called range. Range is like the for X in collection of Python. So you can actually have an iteration over a collection of items, and collections in Python might be a number of things. So might be slices, arrays, and maths. And we will see this later. So basic data types. Right, basic data types. This is quite simple. Go wants everything to be explicit. So you have integer 8-bit, 16-bit, 32-bit, 64, and the same goes for unsigned integer, and the same goes, not the same, but a similar thing goes for float 52 and float 64. number of bits, the size of the type. Fundamentally, there is even an unsigned integer type. There is no float type, which the compiler, which is specified as in the most efficient size for signed and unsigned integer on a specific platform. No safe assumptions can be made on the size of the integer, of course, when you write your code, because you don't really know beforehand on which platform your code is gonna run. So in certain platforms will be very likely int 32 in case of int, or int 64, it depends. Then there are, of course, types for complex numbers. There is complex, and there are functions real and image in order to extract the real part, real component, and imaginary component of a complex number. Then there are bool, which is not an integer. Bool is a type bool. And then there is string. So there is UTF-8 type. UTF-8 is the standard invented by Pike to represent Unicode string. And IOTA const generator. This is something that we can see quickly. We can go over it quickly later on. It's not fundamental. If you find some documentation, you will see how easy it is. Then casting. To cast, there is no implicit casting. In Go, casting needs to be done explicitly, and you can use I can show you this example, the expression type, parentheses, value, which converts the value v into the type t. I'll go over this quickly. Yes, as I said before, unlike in C, in Go, assignments between items of different types require explicit casting, explicit conversion. This is a variable statement. This is a variable statement, and Go took this particular approach. Name of the variable, type, which is quite the contrary of what we used to do. Programmers are used to generally declare the type first and then the variable. But there is actually a reason behind it. The language was designed to be the most human-friendly possible. And human beings tend to define things first by the name and then by the type. So Bob the dog. And of course, it's very unfriendly to see some programmers, because we used to declare type first. But anyway, it's something that you can get around very quickly. And this is a variable declaration. Where you declare var is, of course, a keyword, name of the variable, type, and this is a multiple assignment. Usually multiple assignments are discouraged, but they can actually be used. And this is an example of type casting. So you have a variable float 64, and you need to cast this conversion. In order, you need to cast this variable into an unsigned integer in order to downsize the type into unsigned integer. And I can give an example. If I remove float 64 here, this fails. This is because the function square root from the math package requires floating point numbers. But they are unsigned integers for us, so we need to convert them first before the function can actually execute and successfully. Then arrays, so composite types. Composite types, we are a number of different composite types. There are arrays, then there are slices, then there are maps, structures, and structures are aggregated types, and you will see. So the first type that we can have is fundamentally an array. I need to exit full screen mode again. So, array, this is a variable declaration, items are zeroed. This means that this variable will contain an array of 3 items. Now, arrays need to be sized, otherwise they are not arrays. And the size of the array is actually part of the type. So a 3-item array is a completely different type than a 4-item array. You cannot just cast it. You need to copy, or you need to do the operations in order to downsize or upsize your array. This is an example of the range statement that I discussed before. The range statement returns either 1 or 2 elements. In this case, it returns 2 elements, and the first element is the index of the item that's been yielded by the instruction. So I can run this piece of code and explain. So I is the index, v actually holds the value at the index I of the array. As always, the scope of I and v is just the for block in this case, and they are declared here. Then, if you don't use one of the variables returned by the range statement, you need to declare it empty. This is something that we see in Python as well. So fundamentally, you don't hold the value yielded by the range statement, and if you do, in this case, the compilation will fail, because you get the variable, you declare a variable that you're not going to use within its scope. So this has to be an empty item. And if you don't even use the I variable, then you need to remove the I variable and discard the variable as well. So these are functions. So along with array, I want to introduce functions as well. This is a function statement. Func is a keyword, name of the function, and the signature of the function. Signature means variable name, type. This is a pointer, and I'm going to explain why I use the pointer in order to change the contents of an array. Go is like C. Parameters to functions are passed by value. But when it comes to array, it's actually different than C, because the value in an array is not a pointer like in C. So the array gets copied, gets really copied over, and if I were not to use this pointer, I couldn't be modifying the contents of the array. I just would modify the contents of the array, copy it into the function. The same, it doesn't go the same for slices that we will see shortly. So print array, as you can see, just a function that uses the printf from the format package to print the index and the value, or the index of the array. There is another note here. There is a difference in Go syntax. This is a declaration. So column equals is a declaration, equal is just an assignment. There are certain things I can show you. There are different ways one can declare and instantiate variables in Go. This is a variable declaration. And when a variable is declared but not initialized, it is actually initialized by the language to the so-called types zero value. Zero values, when it comes to integers, 0. For floating point numbers, is 0. For string, is an empty string. For runes, runes is the single character in Go. It's called rune because it's actually not a character, but it's a Unicode code point, and it's called rune. The zero value for a rune is the empty character. The zero value for any pointer is nil, with the type of the pointer. So, and this is quite interesting in Go. When you define a pointer to string, this is initialized to null nil by default, but then you define a pointer to I don't know, to an integer 64. This is nil, initialized to nil, to 0, which is nil. But a nil string is not necessarily nil int 64. This might cause some problems when handling pointers. At times, you might need to cast the nil from a type into another. And so this is a way you can declare variables. Another way to declare and initialize is, as in the example before, I can do this is another variable declaration and initialization. Or, even simpler, you remove var. This is called a short declaration. You declare and initialize a variable. It's pretty common to see this being utilized in Go source code. You cannot use this though in global variable declaration. So when variable is global, you usually use x. This way, you can initialize this way. Same goes for constant. Constant need always to be declared and initialized at the same time. So we can, I think, if there are no questions about the functions, these functions return no return values, but functions in Go, I will go over them later on. Their signatures is func, which is the keyword, name of the function, list of parameters, and then the list of return values. Go functions can return multiple values. And usually one or more values in this return values list is actually the type error, which exists in Go. Go doesn't provide any exceptions whatsoever because Go takes a stance such as errors are valid. And it wants to force the programmer to handle the errors. And I will show you an example later. So arrays can be initialized with this particular syntax as well. So-called literal syntax, which is the size of the array, and then the items you want to initialize. Alternatively, there is another easy syntax, which is 3 dots wrapped up by square brackets, and then you can initialize only the items of the array you want to initialize. This syntax is now supported by C99 as well. So at the end of this statement, the array A will have 100 items, of which the 11th item will be initialized to -4, the 100th item will be initialized to 1, all the other items will be initialized to 0, to the 0 values, because it's an int. And the same goes for strings, and they will be initialized to empty strings. Then there is, arrays are suboptimal when it comes to passing arrays through functions, as we've seen before. You need to specify the pointer, and arrays, most importantly, as inflexible. Arrays cannot be expanded. They cannot shrink, they cannot be expanded any further. So in Go, usually programmers use slices. Slices are very powerful, and they are slices are not arrays, as in slices have properties such as they actually sort of a special type where they are a pointer, a so-called length, of course, and a capacity. Now, by definition, the capacity, given that slices actually sit on top of underlying arrays, so every time you instantiate a slice, you fundamentally have a projection of a portion of an array pointed by a variable, pointed by a pointer. The length of the slice is the number of the items contained by the slice. And the capacity of the slice, given that the slice is a portion of an array, is actually the number of the items starting from the pointer and ending at the end of the underlying array. Now, the way the language, programmers don't need to take care of extending the underlying array. Programmers must not make assumptions on where actually their slices are sitting. So slices are organized and arranged by the compiler according to the demand, the resources of the system, and the program the compiler is actually compiling and running. So this means that you can extend the slice, but you don't know exactly what the compiler is doing behind the scenes. So you cannot really make assumptions. This is an example. So I'm declaring here an array which contains collections of times number, starting from 2. So these arrays size is 7. And I'm now declaring a slice. A slice, the syntax of a slice declaration is very similar to what an array, but there is no size between the brackets. So you declare variable, and you declare the type, of course, and then you can assign the slice in this case. An empty slice, for instance this one, by default the 0 value is nil. And when the slice is nil, length of course is 0. Now I am shortly declaring a slice by, and this is the nomenclature, so even in Python it exists this way, it's slicing the array primes, starting from element 2 up to the end of the array. This means that the slice t, so the slice s contains from the element 1, so from 3 to 7, because 4 is excluded. And in fact the slice S is actually 1357. Slice T starts from 5 and it goes up to the end of the array. And you can print slices this way, you can come up with a function. Slices can be printed because all basic types in Go provide one function which is a string. One method actually. We will see string and the stringer interface later on. So we can see the properties of these slices. For instance, the length of S, which is 3 items, and the capacity of the slice S, which is 6, because it's, as I said, the number of items starting from the pointer till the end of the underlying array. And the same goes for T. The length of T is 5, the capacity of T is 5. Then we have, this is the append operation. Append is quite important. Append is the only way you can append items to slices. There is no method within a slice, like in Python, t append. No, you need to fundamentally create another slice, which will have different length and capacity perhaps as well. So this is pretty easy. This is a new slice called x, which will contain the result of the slice t plus there is 3 items. I'm gonna print x, which is 5, 7, 11, 13, 17, plus 0, 9, and 10. This is a variadic function. Append is a variadic function, so you can actually have multiple parameters after the first one. And I printed x, and then I want to delete item index 3 from this slice. Well, there is no delete, there is no remove function, so there are a couple of ways of doing it. If the order does matter, this is the way of doing it. So you create a new slice by appending from the beginning of x till the item I, and then to the slice which comes after the item I, so item I plus 1 till the end. This is a variadic syntax which exists in C as well. And you happen to have your slice without the item 3, with item 3 removed. This preserves order but it's quite suboptimal because items need to be copied over, item shifted. So there is a way which is swapping the item, and you can like take it as an exercise to rather than doing this, you can actually in two statements swap the item I with the last item in the slice and shift only by one element, which happens in big O n. So it's actually more efficient. But in that case, you wouldn't preserve order of the items, and so this actually preserves order of the items. And this is Go. This is fundamental Go. When it comes to slicing, it's very efficient. As you can see, it's a philosophy of the language. Go is designed to give programmers primitives and building blocks. And no, you will never see any convenience functions in the language to make your life easy. But because most of the time you can actually build your functions, your convenience function that you can use throughout your code. And it's definitely a very easy task every time. So yes, I think, is there any question on the slides? Now carry on with composite types. The next type is maps. So maps are fundamentally hash tables. This is an example of use between slices and maps. Yes. So this function, find duplicate, instantiate a map. This is a way you can instantiate a map by using the operator make. Make is a statement which allows you to instantiate types. So you can actually use a make to instantiate. In this case, you're not instantiating a map, you're instantiating a slice of length 0, capacity 5. Behind the scenes, the compiler will find space in an underlying array for your slice A, and same goes for the slice B, where in this case the length will be 5. It means that this slice will already have 5 items, and I can print them. Slice A, length 0, capacity 5, empty slice. So the length is 0. Slice B instead has been initialized with 5 items, 5 elements, and you have in fact 5 zeros in the slice B. And capacity is 5, and length is 5 as well. So yes, then we want to append. This is the way you can extend your slice. You fundamentally reassign to your slice the result of an append operation to your slice. So the slice B now is going to have length 6 and capacity 12. And extending, because we are going to extend it with one element. The capacity is 12 because the compiler will have found some space in some underlying array, but the length is now 6. Now the function FindDuplicate instead try to find duplicates among a slice of strings. So this is the interesting declaration, which is an items map. So the map is defined this way. Map between, in between square brackets you have the type of the keys, and then you have the type, the type of the value. There could be maps of maps, maps of slices, map of slices, that's not a big deal. And then you can even define a size of the map, which this is not necessary. Maps can also be defined as in this will be an empty map. But when you initialize the map, of course, you always need to when you initialize the keys of the map, in this case it's easy because it's strings, you will need to use the operators square bracket, which means create a new key in the map. Now, this is pretty easy, and this is an important operator in Go. When you access a key in a map, you actually have to, as I said before, errors are important. There is no error return here, but you have the value, which is in this case is discarded because we're not going to use it within the if block. And then you have a so-called OK check, which is true in case the item is in the map or false in case the item is not in the map. So in this case, if look at this, note this conditional here. So you have an instantiation here, and then semicolon, OK. If OK is true, then you return the item of the first duplicate found in this slice of strings. Alternatively, you put a true in the key for that item in the map. If you don't find anything, you return -1. It's a pretty simple function to play with maps. Oh yes, keys of hash tables must be comparable, so to some extent hashable, in order to be used as keys of an hash map. And this is an example, another example of a declaration of a map. So you declare a map, and then you can instantiate it by using this syntax, key and value. This is another example. You can loop over maps, and this is quite interesting. You can loop over a map, but by compiler specification, you cannot make any assumption on the order of the items. Maps are purposely non-deterministic. And in fact, in the Cosmos SDK, you cannot really use Go maps in any of our stores in our state. Because maps are non-deterministic, so it's even very complicated to serialize maps. Then alternative, oh yes, this is an alternative loop, which means this is a for loop. When you iterate over a map, you get the key and the value of all the items, or you can just iterate by keys, and then you can access the value by the square bracket operator. This is another way you can access the keys, as I explained before, and you can say, of course, if the item is not in the map, the value returned is a zero value of that type. So in this case, you have, A is not in a map, int zero value is 0, so you print 0 fundamentally here. And then you can delete items from maps just with a delete operator. So delete takes two parameters. One is m, which is the reference to the map, and the other one is the key you want to delete. And in fact, now the value of the x key in the map is 0, and used to be different. Used to be a minus 344. So then I think one of the last things when it comes to data types is quite important are structures. Structure and pointer. So it's a very simple example. This is a structure in Go. This is the way you define any type in Go. Type, name of the new type, and old type. You can define any type in Go. You can do type x int 64. So x will be now your new int 64 type, you can use it. Needless to say, when you define a variable, actually let's define t. When you define a variable type t, it's not going to be automatically a variable of type int 64. You will have to cast your variable of value of type t into the type int 64. Yes, let's keep an eye on the keep an eye on the watch and shout when I have to finish. Or throw something at me, it's okay. I don't take it personally. So this is a composite type, vector structure, and then you have two variables. One is x of type int, the other one is y type int. Now these variables are exported. It means that they are not accessible only within the methods of this type. We will see method declaration later. I can't really drop a function in here. So anyway, I define a new variable, declare and initialize a new variable type vertex v, and I initialize the variable this way. Now the order does matter, especially when it comes to serialization. So, and I can initialize the vertex this way without specifying the name of the variable, so I could do it this way. And so on. Or I can do either other things like value, vertex, and this will be an empty structure of type vertex. There is no type def unlike C, so when you define a type this way, you just use the type with its name. Now in this case, I also declare a pointer. This is typical C declaration. So I define a pointer to structure vertex, and I store the address of it into P. Then I can modify Px. I could modify anyway Px, but I'm now printing. I'm now printing the variable and the contents of the structure. Now I want to show you how to define a method of vertex. Because now I printed the structure, and what came out was the standard Go representation for structures. But if I were to define a so-called method, methods declaration follow the syntax. Func, of course, because methods are functioning. Okay, this is quite, I would say, not very friendly. It's quite different from any other language, but you define the so-called method receiver, which is the variable. It's like the this or the self pointer in Python and C++. You define, of course, name of the pointer receiver and name of the type you want to attach the method to. I'm going to define a method called string, a public one. Which returns a string as a value, as a return value. Open brackets, close brackets.
Excuse me.
There you go.
It's a little bit late, I know.
No,
Can you zoom a little bit more?
Sure.
The
Is it better?
yes.
Okay. Sorry. I suspected, but I didn't hear nobody complain. So
Yeah,
okay,
but
fine. Carry on.
it's getting more complicated now. So
It's better now. That's fine. So now I can return a string as a string representation of a vector structure. I can put anything I want. There is a function in the package format which is printf, traditional C. So it's printf in C. Instead, I can define my string, my format for my string. So I can do x equals %d, which means integer number, and then I do y %d, and I do big X d1. This is different now. This is because the package format defines an interface called stringer, which is this is interface. We will see interfaces later. So it's a type, but it's a type interface whose type is string, which defines only one method called string. And fundamentally, my type vertex, right, let me zoom in a bit. Sorry, you're right. So stringer is implemented by any value that has a string method, and it is implemented implicitly. So if your type implements a string function which returns a string as a value, then your type meets the interface specification for stringer. And of course, it goes without saying that my print output changed here, because the print family of functions actually use a stringer interface to serialize the output of the types that passed as an argument. So this function, you can imagine, use a object point dot string, go to string function, to string method. That's the way it works. So we will see this better. This is part of the Golang stake on object-oriented programming. You define your types to meet certain interfaces because you want to define behavior of your types. And data and functions live in separate world because they are completely different and they should be treated as such. So, if there is no other questions,
So basically that function, right? The compiler from its parameters, it determines, it ties it to the type, and then, like, I'm coming from an object-oriented. So that would have to be grouped with the type, because it's like you're defining, you're implementing the interface for a type. But this is being done through a function, not through a class. Yeah.
No, this is, so the question is,
I'm just thinking how the compiler is linking that function, you know, as defining how you want to treat that type.
the function println, you mean, printf?
This function you just defined here, the string.
Okay.
How is it being associated to the type? Like, I mean, in object-oriented, it's obvious because you have to group them together. Like,
Okay, you have to group them together as in.
I don't see grouping.
No, there is no grouping. Yes. Actually, yes. This is quite important. Okay, Go packages. I show you an example. I know what's your question. It's actually a very important one. Thank you. So this is Cosmos SDK source code. This directory is a package. Types is our types package. Now, in Go, unlike Python, it's very similar to Java to this extent, much simpler than Python and other languages, where you don't have the separation between a package and the concept of the module. So these files are not modules. They are source files. So anything which exists in the context of this file called context.go exists in the same context of other files organized under the same package. Of course, it goes without saying that these files must have the same declaration on top of the source code. So, as you can see, abci.go got package types, and the same goes for all the other files. Otherwise, compilation fails. There is an exception. And this exception is for test files. Go has this convention. Within a certain package can coexist multiple test packages in order to avoid import loops. So when you actually import cycles, so when you actually test in a package, if you want to test multiple packages, you might happen, if this file were to exist and live within the same package, you might happen to stumble upon an import cycle, and the compiler doesn't resolve import cycle. So it is allowed. It's conventional, idiomatic, but it's the only way the compiler can actually handle this, to have in the same types package directory another package called types_test. In Go, by the way, it's not C-like, it's not Python-like. The syntax is, and this came from Java, camel case, always camel case. There are some philosophical takes on raw Python. This matter, in the end, it's just a matter of convention. So we survived the C, Python, many other languages. So it doesn't really matter what kind of convention you go for. So this is okay. This is quite a nice example. And so this is exactly the same example of a stringer interface, but I can show you, and then we go into interfaces later on. I can show you another example. So I can, for instance, let's say that I want to implement a function called shout, which returns an integer and a string, a method. And it's not really tied to the contents of the object. Actually, I could do something like that, but it doesn't really matter. So this type has now a new method, and somewhere else in other parts of the code, in other component, in the external one, there is a function called I don't know. We can call it. And could be now, this function takes a type shouter, which I haven't yet defined, but I can define it here, which is shouter interface. Now, this type vertex implements implicitly the interface shouter. This function doesn't know anything about the existence of the type vertex. It can take any type which implements a shout method. And the compilation would, of course, succeed. So I can do compilation succeeds. And what else? I can give another thing actually, which is modifying the contents of a structure when it's passed through functions. In this case, you might want to implement a pointer receiver. Pointer receiver, this is quite important. So I want to implement a method which takes a pointer receiver. And you don't need to do anything to dereference the pointer. Absolutely, this will modify the contents of your structure. And you can pass this through the code so that the contents of the structure, because this is, in the end, this is a function, and function takes parameters as copies. So if you want to modify the contents of your structure, of your type, you need to define your methods with pointer receivers. This is different than this. They bond completely different by the company. But you can define both. Generally, when you design a piece of software, you generally decide to only one of these, to only one of the either all pointer
The
receivers.
second one wouldn't update, I think, the vertex, right?
No, this one no.
This
Wouldn't.
is- yeah.
This one of course wouldn't, because it doesn't have a. It's just a function. So it takes a parameter p as a copy of the vertex structure. The other one, of course, would actually modify it. And what else? Oh yes, pointers. I give you this other example, which is quite nice. Constructors of structures. There is no implicit or explicit. You need to define your constructor yourself, and usually a very idiomatic way of doing it, given a type, is to do this. New. Which very likely will take. Oh, this is a short declaration for parameters for functions. So if they have the same type and they have to follow one after another, of course, you can do it this way. And the very nice thing is that you can define a structure here. You can initialize your vertex x, y, this way, and then Go has a garbage collector. But this is not like in C, this will return a pointer to the structure. So when the function closes and the structure is destroyed, the pointer stays there. And it's actually the garbage collector when it goes out of the scope of visibility at some point in your program. But you can return pointers out of functions. And this is unlike C. When you do this, your object will be modifiable. In the Cosmos SDK, since determinism for us in any blockchain application is fundamental, we tend not to use pointers, nowhere. We try to use as few stateless objects as possible, and when we have things like immutable, we try to make all immutable objects as many as possible, and then we make copies of the object when we want to modify something. Objects, or instances. And this is idiomatic. Idiomatic means this is the Go recommended way. You can define a new, but you can actually define multiple vertices and multiple constructors, and you usually want to prepend your constructor with a new. So, okay, I think we can. Is there any question? Okay, I take it as no.
We have to digest.
Yeah, imagine.
I'm sorting my questions.
Yeah, but please. If I'm going too fast.
Just one question. When you had the functions there, you had, for example, the shout function,
Mm-hmm.
and you have a v vertex at the beginning. What's exactly is the purpose of that? Is it a
Sorry.
the function shout, for example, right?
Mm-hmm.
Before it, there is the vertex v.
Yes.
What
Well,
is the
because
purpose of that?
I want to attach the function to the type. I want to make it callable a method. So this is now a method. Actually, as a matter of fact, since I'm not using the pointer the method receiver in the method, I could actually do this. Which makes it even more readable to say, hey, this is a method of this type, but I'm not using the contents of the type. And but of course, this doesn't make much sense, as in, why should I attach this, given that I'm but it's just an example snippet, of course. But of course, this makes the type meet the shouter interface.
So if in the main method you write v.shout, it outputs hey, am I understanding correctly?
Sorry.
If in the main function, okay, you write v.shout.
Yeah.
That will work and it will output hey.
Shout me here. So I say
Both.
sorry. Yes, I'm basically taking. Yes, you're right. Because I can do this. Actually, I forgot one thing. This would work. And the type check would pass, because I'm taking a type variable is s, value would be a shouter type, and I make the assumption that it meets, of course, the shout interface. The compilation would fail in case it wouldn't have a shout method, and I can give you an example. For instance, I want to call this function shout2. Now the type vertex doesn't meet the shouter interface anymore. And in fact, compilation fails. Because the type can use v, so line 43, shout me, passing v as an argument, because type vertex, I can use type vertex as type shouter in argument to shout me. Vertex does not implement shouter, missing shout method. Because I renamed the shout method to shout2. Now, this doesn't happen when it comes to println, because the print family of functions have a way to always serialize a basic type in case there is no string compliance. So of course it tries not to make things fail because you didn't define a string method. But this is what happens. I could actually, yeah. This is actually this happens because prints this, but it wouldn't fail had I not be defined a string method, because structures, the type structure actually have a string method defined by default. Of course, this is a basic type of the language. So if there is no string method, the language actually has a string representation for the basic.
You're like overriding it.
Yeah, kind of overriding it, but of course, because the structure has its own default method for it, because it's a basic type.
Is there overriding in?
No, there is no overriding. There is no overriding, but there is composition. I'll show you.
So I cannot have like two functions with the same signature, but
Absolutely not. It's forbidden. It's like blasphemy for the designers. No, seriously, but the language, of course, it's a completely different take on programming. So errors have value. This is quite interesting. So no exceptions. I'll show you an example later on. This is an example of anonymous functions. I import here the package strings, which contains string manipulation functions, like for instance, a string map. The strings map, we go to the strings package and read the documentation about it. Returns a copy of the string S with all these characters modified according to the mapping function. So if characters, of course, runes, so characters. If mapping returns a negative value, the character is dropped from the string with no replacement. And so yeah. And fundamentally, I'm passing this, which is an anonymous function. So it's not declared anywhere, just a sort of a closure. This modifies every single character of the string I have 9,000 by incrementing the value of the character, or the rune. Because the rune, the character, is actually a Unicode code point, like ASCII characters. Then we have defer. Okay, this is go by example. This is quite interesting. Defer is a keyword, a statement which allows to define a function, to define a function call that will be called at the execution of at the end of the execution of the current block. So, for instance, function main here. Let me zoom a bit. we use a function called create file to create a file called defer.txt, an example piece of code. There is a call, of course, in the package OS to create a file. The creation might fail for a number of reasons. For instance, because the file existed already, or the disk is not accessible, etc., etc. Now, this function returns either a file pointer and an error. Errors are value. So when you receive an error, you need to check whether there is an error and handle it accordingly. And this is the function panic. Panic, we will see panic later on, but panic, when you have an error, the coder, the programmer is supposed to handle the error appropriately, which might be logging, which might be finding a solution, a retry, or whatever, or maybe just transmitting the error upstream, whatever. Panic in Go by default causes the program to halt. So it's like, this is an unrecoverable error. I don't know how to go about it. So I'm gonna crash, trying to make as much noise as possible.
It's like
Printing stack trace, etc., etc., etc.
it's like throw.
Yes, it's like throw, but it's a very strong throw, because in order to handle throw,
It cannot be handled at another layer in Panic, no?
sorry?
Throw can be handled.
Throw can be handled.
But panic, no.
Panic can be actually handled by the function recover. But of course, the language is designed as such that you should not really use panic and recover until or unless the error is really, some inconsistent thing, some inconsistency in the universe or in the time space, and you can't really recover that. Actually, there are some strategies, especially in, of course, distributed systems, when errors, weird errors and unrecoverable errors might happen, and you actually need to recover from them.
You restart the server.
There might be a restart. There might be a restart of a so-called coroutine, which is a coroutine. There might be, there might be a way you want to handle that error. But that's why panic and recover actually works. But they need to be used with caution, because the coroutine or the execution context in which the panic happens, it might be disrupted. So you really want to handle errors rather than handle panics as much as possible. So defer, we were talking about defer. This create a file, assuming that the creation happens and there is no panic. Then at the end, after you got the file pointer, you say close file. So it's a function call, but you say don't call it now. Call it when the function I've been executed within exits, before it exits. So the right execution of this is create file, write file, close file. And you can actually call defer multiple times, and defer execution order is reverse. So the last defer function is actually the first is going to be executed when the function closes.
Does it really matter where the defer is put in the code?
Yes.
Can you put the first one? It's just like a stack. Okay.
Yeah. And even here, close file. Of course, in this case, because of the design, when this needs to when this needs to be closed, when there is an error in closing the file, just exit. Fair close file. Oh, of course. It's a program designed to panic, so this will not be executed ever. Because the first panic makes the program crash. And the argument of a panic would be a string or could be an error. So that doesn't really, it doesn't really matter. Then recover, that we talked about before. Okay, so there is a call to f. F is a function. At the end of the execution of f will be called this function, which calls a recover. So calling g, some logging, g gets called. After 3 iterations, g fails and panic, so this function closes. So after the panicking, there is a defer in G, there is another defer in G, there is another defer in G1, because after the panic, all the defer instructions get executed. Until there is a recover. So panic is a controlled way to panic from a program. It's not like a SIG 7V. It's not like I'm sending a SIG abort. It's a proper controlled way of panicking. So in case there are multiple recover functions, they will be executed. Multiple defer functions in order to close appropriately, correctly, to handle panics correctly, defer statements will be executed.
It's like finally.
It's like finally, and it gets executed unconditionally. And yeah, that's correct. So it's a recover. Go on.
So if you have several defer functions, and in one of the defer functions you have a recover, and
yes,
and the panic is called before, the recover and the defer function continues processing the program.
Okay, that's the way it works.
Okay.
You define a defer function code, so that you know at the end of your function, your execution scope, there will be a recover somewhere. So in case something panics badly, you know that at the end of your code, you will have a recover code. And then recover returns the error thrown by the panic, so that the recover in F, and in fact, the panic thrown by the function G, it's fundamentally a string representation of the number 4. The recover call here yields a return value, which is R, and R contains the string 4. So you can actually still, backtracing the message to the backsending the message to the recover call. So now, let's talk about inheritance, which doesn't exist in Go, but there is embedding, and therefore composition. So this is a structure, a point, we saw vertex before, but this is a structure of, which contains 2 variables, 2 members, one is x, the other one is y, both are float 64. This is a short declaration of a structure. Of course, the order always does matter. And then there is another structure called color point. Now, color point embeds a structure type point. This is anonymously embedding point. So there are 2 ways you can embed a structure. One is a type. One is doing it this way. Color RGB. I can actually show you the package color. Yes, images. Color. Image color. Sorry. It's a type, but it's an interface which provides a method which is RGBA and returns, of course, 4 components for unsigned integer, 32-bit unsigned integer. So color point is embeds point, as in anonymously embedding point, as in this structure will kind of inherit X and Y, but it will not inherit, it will just contain a reference, an anonymous reference to the point structure, to an instance of a point structure. And this is another point structure containing a pointer to point, and you need this in order to modify X and Y of the embedded structure. And then you can call all the methods. You can call distance. You can call scale by. But scale by, of course, in order to work properly, has to be given a pointer 0. Otherwise, you cannot modify the binary members. Encapsulation, as we said before, anything whose name starts with a capital letter A is exported, anything else, all the rest is actually private, so it cannot be accessed if not within the same language. Then what else? Let's see. Let's carry on. Oh yes, interfaces. So this is fundamentally the take on object-oriented programming by Rob Pike. Rob Pike and Joe Armstrong and Kernighan. They say data, one of the most messy, this is arguable, I'm not saying that this is truth, but one of the most arguable points of object-oriented programming, one of the most prominent mistakes was to make classes as a sort of mixed type, so one can mix cherry-pick data and functions and make them living together. Whilst data and functions are completely different, they should live separately. And so the concept of having this quite sharp distinction between data types and interfaces and functions as in piece of logic actually takes, it comes from the fact that, philosophically speaking, a function can be defined a function can be read and understood by just looking at the parameters and the return values. So you treat it as a black box, you don't necessarily have to go through the code to understand what a function does. You can just take it as a black box and say, okay, this function fundamentally transforms inputs from a type T into outputs from a type V. And they should handle as less data as possible, and whilst the data can be defined as something. So functions do things, whilst data just is. And this is fundamentally the take on object-oriented programming. And a Go object-oriented model helps solve the circle ellipse problem, where one of the most problematic points with object-oriented programming was inheritance, as I said before. Because inheritance is usually taught using real-world metaphors, like this example, apple and orange are subclass of the class fruit, which makes sense in real world in a classification made by humans, but carrying this way of thinking into programming might be dangerous, because objects should be modeled according to applications requirements rather than taxonomical structures or hierarchies that might make sense to humans, but might not make sense. They actually might create more problems when it comes to practice. So the circle ellipsis problem is quite a known one, square rectangle problem, where you can't really define either a subclass of another in practical terms. and you happen to either redefine all the methods, or most of them, and so you can't really define a relationship between a circle and ellipses in practical terms when it comes to programming. So the interfaces come from this take on object-oriented programming. Interfaces define types, behaviors. And as I said before, they are satisfied implicitly. The I/O writer interface is actually a very interesting one. I can actually show you this relation between the printf family, fprintf family, and I/O writer, which is quite interesting. It's a very simple one, of course, it's basics. I think wireless down, okay, it's working. So the fprintf function, like the C traditional fprintf function, takes, in C will be a string, here will be actually a file pointer, here is a writer. A writer is an interface defined as one function, one method called write, that takes a byte slice. Byte is a alias for unsigned integer, and then we have 8-bit, of course, and then we have two return values. One is the number of bytes written, the other one is an error. And the format fprintf function takes a writer as the first argument, and then format string and a variatic number of arguments, so that one can actually append as many arguments. I mean, printf family function. Interface is a particular type. Interface is a type of interface, but empty interface is the empty interface type. They can be easily casted. Actually, any interface can be easily cast and converted into an empty interface type, so that these can take anything. It's very similar to what in C is a void pointer. And yeah, that is true fundamentally. So, this is a type assertion. It's quite important when it comes to casting and converting types into others. There are type assertions in Go, of course, because at runtime you might need to check what actually you're dealing with. So this is an interface, and it's quite generic, so that you can accept even a string. And then you cast you do a type assertion from the value stored in the variable I, and you type assert is actually a string. This is a syntax. So variable dot parentheses type within parentheses, and it works. In case the variable I didn't meet the interface string, this will panic. So that's why there is another syntax, which is new declaration, new assignment, so new variable, okay. In case the variable I, its value, didn't meet the string type, it wouldn't fail, but okay, it would be false. So that you can actually type a set without making your program fail. Ditto here. So this print false, because a string cannot really be turned into a float 64-bit, and in fact the f is initialized to its zero value, to float zero value, which is 0, and printed false. But then if I force the type assertion, then the program panics. Oh, this is quite interesting as well. So I declare a variable of type writer, which can host any type which implements the writer interface. Also, standard out does implement the writer interface because it's type host file pointer. So this is actually the same thing. And even though f now will be of type pointer to host file. This will panic because although bytes buffer implement no, this panics because bytes buffer doesn't implement the write function. That's why it panics. Type switches. Okay, this is not an important thing. Other than type assertions. Type switches. Let's see, I need to copy this. So yes, this is a way so that you can actually have multiple type assertions in series, and the syntax is a switch case. So you have switch destination variable and type. So variable interface of type. As you can see, this function takes a generic interface, an empty interface, the most universal data type in Go. And you're gonna check type by type which ones that meets. And the first that it meets it, of course, the execution flow stops and goes out in the switch case.
So it can check by type.
Sorry?
I'm saying right that the switch case can check by type.
Yes, yes. Check by type. So
It's not like, for example, having a value, checking a value. The traditional switch case, for example, is
no, this checks type by type.
you can check types instead of values.
Correct. You check types instead of values. Correct. So in this case, I call do with 21, and it will print. Well, I just run it because in this case, v is casted into an int, so you can do v by 2. So twice 21 is 42. This is a special descriptor. This means print it anyway, print the value with interface. There are a number of different format descriptors in Go. Most of them are actually like in C and Java, but this is a special one for Golang. And this works with the structures as well, by the way. This works pretty well. So it actually prints the content of a structure. And then I pass hello to do. The type of hello is a string, so it will enter the case a string and print hello is 5 bytes long. Alternatively, if I don't handle the case where the type could be Boolean, go into the default case and say I don't know about type bool. And you can print the type of a variable by utilizing this syntax here. The name of the type.
That is determined by the compiler then.
What?
The type.
Yes.
The type of the.
Yes.
Because you're passing into a function. So.
Yes.
It's a bool.
This is a literal argument. I'm passing an argument. Of course, this is determined by the compiler. Yes, of course. Our compilation time.
But still, the V, you are comparing the strings there. The types.
Types.
But still, the value is returned into V.
Yes. In that case, yes, because your type asserted. So V will contain
the value.
The value in the type of the case.
And the case will check not the value, but it will check the type.
Correct.
And then
assign
the value.
It's just a very short form. Yes, but it's correct. You cast that interface into another type, into a concrete type. And so yes, useful to test the value against different types safely without causing necessarily panic. But you will see, it's quite common in Go code to have a panic here, because I don't know what you're passing to me. I just panic. Or I return an error. Now concurrency. Sorry, I need to check.
Concurrency?
And
You learned concurrency? On 101? Doing that advanced topics?
yes.
I mean, we could. It's how many weeks ago?
Concurrency is pretty simple and go. We can. Yes. You take a break, right?
As you wish. I mean, maybe ask. It's like, I don't know.
During the break,
I
you want to take a break?
Bathroom and something.
Yes, let's take a break. Let's take a break. Okay? Yes.